So today we are going to talk about this Asian options and look-back options. Okay. So for Asian options and look-back options, there are another two types of path-dependent options, just like barrier options. Okay. But in the barrier options, there won't be any troubles like that because the barrier option, the path-dependent feature is kind of weak. And it only depends on whether this barrier is hit or not in the previous in the history. So that actually is very easy to handle. But in Asian option and the look-back option, this path-dependent feature directly shows up in our parallel function, either through A or G or this MT, the running maximum, running average, this integral, whatever. So it's kind of hard to deal with. And that's also why when we write down some PDE formulation, we will see this function v will no longer only depend on t and s, it will also depend on something else. Okay? This additional variable will be introduced to capture the historical behavior of this dog. Okay? So that we have to remember what happened in the past. Okay? Otherwise we cannot write down these PDEs. Okay? So let me just talk about the PDE formulations, because in very rare cases we can find a closed form. Okay? And when we do that, it's also very tricky. But our questions won't relate to that. But anyhow, I will just talk about this PDE formulation, just to give you some ideas about how do we derive this PDE. So my one word conclusion for this PDE is here. So this PDE will just come from Ito's lemma. Okay, all this PDE formulation comes from Ito's lemma. So how do we get that? So say V is our price. Okay, V is our price. I'm not sure, I don't care for now what this V function depends on. So let's say it's TST and perhaps it's some other variable XT. So since V is the option price, is the price of some derivatives, then based on the non-arbitrary principle or the risk neutral pricing theory, the discounted asset price, the discounted option price will be a Q martingale. Okay, this guy should be a Q martingale. Okay, it has to be the Q martingale. No matter what is this X, what is this VU, what is the option is. So it's always a Q martingale. Since it's a Q martingale, then we know basically when we apply Ito's lemma, there should be no more DT term, or there should just be DWT term. Okay? So we apply Ito's lemma to this guy. Okay, discounted option price. Then I'm writing down this as an integral form. Okay, but if you if you ignore this initial value, ignore this integral form, what's inside here is just the Ito's lemma. Okay, it's this differential form in Ito's lemma. So if we do that, we got this partial v partial t dt, partial v partial s ds, and minus rv dt. That comes from this discount factor. Okay, and also the first order derivative with that x at dx. And we are not done yet, since here it's just first order expansion. Okay, so that we know we have to do the second order. That gives us a half partial v second order derivative with respect to x dst. And then in some cases we still need to work out the second order expansion for x as well. Okay. So that's really depend on what is dxt. So the impact of xt will shows up here. So what is this xt? So in the case of Asian option, no matter it's arithmetic Asian option, running average AT, or this integral IT, or the geometric average GT, no matter what this x is, we always have this kind of when we do some Ito's lemma for that, we will always find out this dxt can be written as something dt. Okay. We will always say that for Asian option here. So once we have dxt can be represented by something dt, then we know dxt, we do not need to expand further for xt. It's just the first order. Also, there is no cross derivatives. xt dst is also too small. So it's there. And finally, we know, so if we combine in this dt term, because we know dst will have dt dwt, and dxt is simply dt, and the dst is again dt. So we finally will have something dt plus something dwt, and everything under this integration. Okay? So that we need to make sure everything, this guy is a Q martingale, so that this term has to be zero. It has to vanish. Okay? So if you combine all these terms under this integral using Ito's lemma and then combining them together, you will see this dt term exactly this guy. Okay? This term contributes to dt term when we do Ito's lemma to the discounted asset price. Okay, we set this guy to be 0, so basically we require this dt term to be 0, then it will become a martingale and then everything should be fine. It should be consistent with our no arbitrary framework. So that's how we derive that. Actually, we follow the similar procedure when we derive the PD formulation for this loopback option as well. Everything should be the same. The only difference is when we take xt to be this running maximum or the running minimum, in that case, DMT, okay? In that case, this DMT. DMT is actually a bad thing itself. MT itself is, we cannot write this DMT as anything DT. Okay? There is no such representation. DMT cannot be written as something DT term itself. Okay? This running maximum cannot be written as DT term. So that we need to revisit our procedure here. So that means this dxt. So let me replace xt by mt. Okay. This is m, this is m. So if we repeat this procedure from here to here, when we reorganizing every terms, the only difference will shows up that this DMT term is so unique. It cannot be classified to DT term. It can neither be classified into DWT term. It's just a unique here. Okay. So then we are still fine. Ito's lemma is still there. It's still fine. So DT, DWT, etc. We have this actual DMT term. So we still the idea is the same. We still need to make sure this is a martingale term, so that the only DWT term should remain. These two terms should both of them should vanish. Okay, it should be still this DWT term. Why is that? You know, this integral with respect to DWT will contribute to a martingale term, right? Or you could say, since we know there are multiple representation theorems, so as long as it's a martingale, it's always just DWT. There are multiple representation theorem is never about DT, DMT whatsoever. It's just about DWT. Only DWT should be 0. So that we still need to require this DT term to be 0. Okay. So once we do that, we will find out this equation. Okay. Since there are still 4 old terms as in the vanilla pool European electrons equation, that's because when we do this all Ito's lemma thing, it will be the same thing. It will result in the same thing. The very special problem arises in this DMT term. That's because really DMT is a very special guy. So what is DMT? If we think about this, what happens about this DMT? So this is stock price. Actually, this is a very bad stock price. Okay, let's say this is stock price. Okay, so if we keep track of the historical maximum, you will see for perhaps the historical maximum, it could be this term. Okay, this dashed line will be the historical maximum. So this DMT, you will see the historical maximum can only increase. Okay, the best performance, the highest peak of the stock price can be updated to a higher level. It cannot be anything lower. So DMT is always greater or equal to 0. MT is increasing, so DMT is always greater or equal to 0. So this guy, so there are 2 scenarios. The first scenario is DMT is 0. It happens because if you look at this path, in many regions, in many cases, this dashed line is just flat. The historical maximum will not be updated. Okay, the stock price is actually underperformed relative to its historical maximum, so that DMT will not be updated anymore at this moment. So DMT is 0. So in this case, when this happens, this term automatically becomes 0. Okay, we do not need to worry anything because DMT is 0. So DMT multiplied by anything is 0. So we are fine. We do not need to require anything about this term. Actually, this term is nothing but partial V, partial M. We do not need to impose any condition on partial V, partial M when DMT is 0. But it could be the case that DMT is larger than 0, strictly larger than 0. That's the case when we really need to say something about this partial V, partial M. Okay? We need to make sure that this term will vanish no matter what, so that we need to make sure that partial V, partial M should equal to 0 when DMT is larger than 0. Okay? So let's see what will happen. So under what condition DMT will be larger than 0? So my claim is, and the conclusion should be, DMT is 0. DMT is larger than 0. It's strictly larger than 0. Only happens when the current stock price equals to the historical maximum. The heuristic is here. So let's say this historically. Let's say this M. This is the current moment T. This is the historical maximum is here. As long as the current stock price is strictly lower, than the historical maximum. Okay? As long as this is the current stock price. As long as there is still some gap, some positive gap between the current stock price and the historical peak, then we still need to wait for a certain moment or a certain period to wait until the stock price goes up and crosses value. Okay, crosses the level M. Okay, we still need to wait some time, wait for maybe some time to make sure that the stock price may maybe go beyond this historical maximum level. But we always need to always need to wait for a certain period. Okay, we always need to stay. So that means at this moment, the historical maximum will still be M. It will not jump up. It will not be updated because the stock price is still strictly lower. So it's still we need to wait for some time to wait for this stock price to go up. So if the stock price is strictly lower than M, it's still 0. DMT is still 0. DMT is still 0. DMT is strictly larger than 0 only happens when stock price equals to current stock price. The current stock price equals to the historical maximum. Okay, that's the only cases. Okay, DMT is strictly larger than 0 only if the current stock price equals to the historical maximum. Okay, that's the only scenario when DMT larger than 0 happens. So that our requirement, the condition or the constraints we impose on this partial V partial M should only be about when S equals to M. Okay, the constraint about partial V partial M will only be binding when S equals to M. So that's why we have this additional boundary condition when S equals to M. This is just one way to interpret why we have this equation and also why we have this boundary condition. Okay? So just one word about this notation. So this notation, it means that we first calculate the partial derivatives. Okay? So V is a function of T, S, and M. Okay? We'll first compute the partial derivatives with respect to the third argument. And then we just plug in T, M, and M. Plug in this number back to this the first and second and third argument. Okay, derivative first and then plug in the number. It's not about plugging in the second argument by M and then compute the derivatives. It's about first the derivatives and then plug in the number. Okay, so that's my way to explain why we have this boundary condition M. Okay, so that's something I want to talk about. Okay. So I suggest we should look at first. We should look at these questions first. Okay. So the first question is about an arithmetic Asian option. Okay, arithmetic average Asian option. So it's AT, and we know the payoff and it's the price. And for what we are going to do about this question is we are going to do some transformation, just like this Rogers-Shi method. To get rid of one variable here. Okay, so the transformation we are going to do is about this R equals to this guy. And the first thing we need to do is find out with DRT, and then we are going to do a lot of transformation to find out the price, find out the equation for H and what is Y. Okay, anyhow, let's look at the first part. So this part, to find out this DRT, this differential form for RT, is very similar when we derive this equation to find out DAT. The technique is very similar. So based on our past experience when we work on this AT DAT thing, perhaps it's ideal for us to first introduce this integral u du. Okay, we introduce the IT and this integral as some intermediate steps so that it will help out to simplify this computation. So that if we do that, we'll realize that RT is nothing but IT over ST. Alright? So that's the integral of IT over ST. Alright? So RT is nothing but a function of I and S. And both I and S are just two Stokes process. So it's just a function of a Stokes process. In order to find out the differential form dRT is just a multivariate Ito's lemma. Okay, Ito's form, multivariate, of course. So in order to do that, we need to pin down first what is dST. So dST is geometrical motion. Nothing to say. What is dIT? What is dIT here? So if you still remember, actually this is one of the tricky questions I left for you when we first talked about Ito's lemma. So this integral form is equivalent to this differential form. Okay? It's just like this fundamental theorem of calculus. So differential form and integral form actually it means the same thing, alright? Actually it's not the fundamental theorem of calculus, but anyhow, it's just this differential form and integral form. Actually it means the same thing. Okay? So there is from this kind of equivalency actually does not come from any Ito's lemma. It's not no Ito's lemma here. It's just a plain language. It's just a simple definition of that. Okay, it's just a notation, you could say. It's just a mean the same thing. So there are no such thing as second order derivatives or whatsoever. So it's just the equivalent. Okay, so that's dIT. So dIT is either dST is just a geometrical motion thing, and will be fine. Okay, and just one thing. So dIT is equal can be written as something dt. So we know that we do not need to expand the second order with respect to I. Also, we do not need to consider the cross variation because dt is already small enough. So we apply multivariate Ito's lemma. So this is the derivative with respect to I. This is the derivative with respect to S. Since it's a 1 over S thing, so it becomes minus 1 over S squared, so ds. And the second order derivatives with respect to S. Alright? ds, okay. And we're plugging in all these things we know and to simplify and basically we can now with this dRT here. Alright? So that's the first part. And so the whole procedure will look like very similar to what we did in a lecture when we try to find out this dAT thing. It's very similar. Okay, dRT, dAT, similar. Okay. So this is that's it. And then second part, we are going to show that this payoff function can be written as the stock price as t times the function of R and t. Okay. So to rewrite this payoff, the terminal condition is always easy because terminal condition is just st minus at. And we already know our target is to write this guy as st times something. So let's say why not just bring this at out first. And this becomes 1 minus at over st. Takes positive part, alright? So it's just left here, at over st. So what is at over st? So at over st is not the good terms we want to keep because we want to keep rt and t, not at and s. So let's go back here. So what is at and what is at over st? So that at over st will becomes, so at will becomes 1 over t, this integral. And of course over st. So we got st. So if you, let me write st on the right. Okay. So if you observe this kind of form, you will see if you combine this part, it will give you rt. Okay, rt is about this integral over st. So this observation is here. So this part is actually rt. Right. So this st times 1 minus. So you see at over st just becomes rt over t. So this rt over t, and positive part is still there. So that we can identify this h. So this h function is just this function. Okay? That's the function. This is the h function. So that's it. Okay, that's a payoff. So inspired by this kind of decomposition of v can be written as s times h of r and t. So we can try out some transformation here. This v, we try to write v as s times h of r and t. Okay, so we are going to find out an equation with respect to h. Okay. So how do we do that? So we know v satisfies some Black-Scholes type equation. Okay, there are 5 terms in the equation for v: partial v, partial s, partial a, partial b, partial a, partial b, partial t, and etc. Okay, so we need to compute all these partial derivatives one term by one term, and to express them as something related to h. And then we can do some substitution and simplification. And just one thing to notice that this value is R. Actually, R is a new variable, so we introduce here. Okay, so we need to find the linkage between R and SA and T. Okay, so if you look at this R here over there, R equals to this integral over S. So if you like, you can just rewrite this R as T times A over S. Okay, R equals to T times A over S. So A is the average divided by T. So we multiply by T, it becomes this integral. T times A corresponds to this integral, and of course over S. That's R. Why do we need this linkage between R and this SA and T? That's because when we calculate the derivatives with respect to S, and S here and also R actually depend on S. So we really need to pin down the functional form of R, how R depends on T, A, and S. So we need to pin down this functional form. Anyhow, this functional form is just T times A over S. So it's all simple. And then it just comes our calculus. So this calculus is very painful, I guess. You got so many terms, and you need to find even a second order derivatives. But if you did it right, then basically you can end up with this equation too. Right? So I guess I will just skip this whole calculus calculation. Okay? It's nothing technically it's nothing difficult here. It's just very tedious calculus. Okay? Chain rule, product rule, and this sort of stuff. Okay. Anyhow, that's the equation, right? So the last part is about finding the boundary conditions and the terminal conditions about this equation H. So there are three parts. There are two boundary conditions, one for R goes to infinity and another one for R goes to 0. So actually, these two parts can be very tricky. That's if you still remember my comments last week, the boundary condition at infinity and 0, they are very, very hard to pin down. It's not natural. We need to impose some artificial boundary conditions to make sure our imposed artificial boundary condition is still consistent with this equation. Okay, it's just very hard. It's very challenging. Okay, it's not a natural boundary conditions. So what do we mean by natural boundary conditions? So let me see. So if you think about some scenarios in physics, you will know there will be some boundaries, and the temperature on this boundary is a constant. So that's a natural boundary condition. It's already there. But if you think about the artificial boundary condition, it's like this. Actually, we know nothing about this boundary behavior. So we really need to do it by ourselves. So that's why we make these two boundaries very tricky. But anyhow, this terminal condition is very easy. Okay, the terminal condition is easy because we have already worked that out. Okay, in part B, the terminal condition is this guy. Okay, this is the terminal value. This is the terminal condition. So the terminal condition is very easy. We already found that in part B, the terminal condition is R over T. Okay. So that's the terminal condition. So let's try to find out the boundary condition, infinity and 0. So let's think about the boundary condition. So how do we specify the boundary condition at infinity first? So how do we do that? So if you recall what we did in last week for the barrier options, or even for the vanilla put Black-Scholes equation, and actually we need some asymptotic argument for this behavior when R goes to infinities. So usually that will depend on our pair structure. Okay, that will depend on our pair structure. For example, if we are having a put option when the stop price is so high, then basically the put option will worth 0. Okay, when the stop price is very, very high, the put option will worth 0. So it's similar here. Even though this R itself is not a stock, but we can always regard it as some sort of stock. Okay, so this guy, when R is very large, then the terminal value for this contract is very, very small. It's just almost surely to be 0. Okay, when R is very large at the moment, then basically R cannot be so small at terminal value, so it's almost surely to be 0. In that case, the terminal payoff is 0. Then we can guess at least the initial value should be 0 when R goes to infinity. Okay, that's our condition. That's our boundary condition when R goes to infinity. Okay, so the boundary condition should be 0. That's our guess at least, and that's our some intuition related to that. And what about this boundary condition when R is 0? So it's also tricky, but it's easier to handle because comparing to this infinity thing, 0 is actually a real number. Okay, 0 is indeed a number. So what we can do? We can just by trying to plug in this r equals 0 to this equation to see what this equation becomes. Okay, so we plug in r equals 0 to this equation, r equals 0 to this equation. It seems that like this term becomes 0, then this term becomes 0. Okay, r is 0, so this term is gone. And r is 0, this term is gone. And what's left is just partial h, partial t plus partial h, partial r. That's exactly the terms we are looking for. Okay, that should be 0, as implied by this equation itself. Okay, r is 0, and this term is 0. So partial h, partial t plus partial h, partial r equal to 0. It seems that this it should be true, but actually this whole argument is not so rigorous because for the infinity case, you really need a lot of argument to prove this limit is indeed 0 or what. And also, this is even more dangerous. It's more tricky when r is 0 because if we look at this equation, okay, this unknown function h, we really do not know what this h is. Okay, it could be happen that this partial second order derivation with respect to r could go to infinity when r goes to 0, right? Because let's say r is log r, sorry, h is log r. So when we take the second order derivatives, it becomes 1 over r squared. 1 over r squared. So if you do this multiplication first, you will see it's just 1, it's not 0. So it could be the case because we never know. At this moment, we never know what is h. So our argument just by plugging just the r equals 0 there and get rid of this term is very, very dangerous. Okay? This is not a very rigorous way to do that. So in order to do that rigorously, you really need to first estimate this equation, what this r is, and what is the value, what is the possible values for this kind of derivatives. And there is a lot of work to be done. But luckily, at least given our context, these are this kind of heuristics. So what I just presented before is just about some intuition, some heuristics. Okay, all this heuristic works. Okay, we are lucky under our scenarios. So for example, if r goes to infinity, our heuristics tell that it should be 0, and it turns out it should be 0 after a lot of rigorous justification. And also this is the same thing. Okay, well, we can just replace replace r by 0, and what this equation reduced to is just our one condition. Okay, it is not so rigorous, but this kind of heuristic often works. Okay, this kind of heuristic often works. So let's just stick to that. Okay, because this course is not really about PD. It's a very, very deep series in PDs to argue this kind of boundary behaviors. Okay, anyhow, so let's just deal with this simpler way. Okay. Okay. So that's this boundary conditions. And question 2. Question 2, I guess, is very, very similar because actually we have seen this kind of question many, many times. Since we know some functions satisfy some equations, and then we can do some transformation, and we can derive a new equation for this new function. Okay, so I won't talk about the details about that. So if you do it, you know, it's chain rule, product rule, and all these calculus, partial derivatives, plugging everything, and you simplify and get it. Okay, but the point I just want to mention is this. So actually, this question is about geometric averaging option. So in our lecture, I think that we just derived this closed form solution of the fixed strike geometric Asian option. So in that case, we didn't talk about this PDE. So perhaps a good idea is you can try to derive this PDE yourself to see whether you can derive this correct PDE formulation for this geometric parameter. Also for this geometric average Asian option. Okay, to see whether you can get this equation right or not. Yeah, either by but the case in later you'll see the k ingredient to derive this equation is still to find out what is dJt. Okay, it's really about what is dJt is. Okay, what is dJt is. Later you will see dJt can also be written as, I believe you can also written as dJt equals something dt. That's why you just result in this kind of term. It's very similar as this kind of, formally speaking, is very similar to this arithmetic average Asian option, right? Because it's one more additional term compared to our classical vanilla your Black-Scholes equation. Anyhow, I guess you can try to find out this term. Okay. But anyhow, for this question alone, it's just a calculus. You see, it's very, very tedious. And technically speaking, nothing serious here. So I'll directly show this answer and skip this whole one. Very, very complicated calculation. So the final equation will look like this way. And yeah, if you do it right, I'm sure you will get this the correct equation. At least you will see, indeed, there are only y there, y and t there. Okay, the additional variables will get cancelled. Okay, so that's question 2. And of course, terminal condition is actually pin down this terminal condition is very easy. Just looking at the terminal payoff and do similar transform as implied there. So anyhow, and the look back option, I have already talked about a lot about this look back option. And also, if you like, you can also try to think about some American type formulation for both Asian option or this look back option. Anyhow, let's do the questions. So these questions, question 3 and 4, actually they are not very difficult. Even maybe you are not so familiar with this PDEs and this how to compute this look back option in closed form, it does not matter here. Okay. The only thing you need to know about this to solve this question is that no arbitrary principles or the law of firm price, and also as well as this payoff functions of this kind of options. Then you can do it. So you see, for example, for question 3, we are going to prove some relations between the call option price, some kind of call option price, and some kind of put option price. So it just reminds us of this put call parities for vanilla European cookies. Okay. So if you try to recall what do we prove there, how do we prove that in the very beginning? So actually you'll see the only thing we need to do is try to construct some portfolios and by using the arbitrary principle. Okay, that's the only thing we need to do. So same thing here, almost the same thing here. So let's say we are going to prove that this value, the price of this guy minus the price of this guy equals the stock price value of this guy. So let's just call the left hand side to be our portfolio A, and the right hand side to be our portfolio B. So the only thing we need to prove is the portfolio A and the portfolio B always have the same value at any time t. So it is sufficient for us to just to prove that these two portfolios have the same value at maturity. All right, that's the law of one price. If two portfolios have the same, it's 100% sure that these two portfolios have the same value in the future. So at any time before that, it should always have the same value. That's the law of one price, or the no arbitrary principle. So that's something we are going to do. So let's say this is portfolio A, this is the portfolio B. So we are going to verify whether these two portfolios have the same value at some future time. And of course, under this context, the future time should correspond to the terminal time. Okay? It's the maturity time. So let's look at portfolio B first, because portfolio B is it's much easier. It only consists of 1 unit stock and this amount of cash at time t. Okay. Then at time t, the stock price will become xt. Okay, that's 1 unit stock, and this amount of cash will become minus k dollars. All right. This is the amount of cash at time t. So after some interest rate at maturity time, it becomes minus k. Okay. What about portfolio A? So portfolio A consists of this kind of call minus a short position in this kind of put. So what about the payoff of this call option? So it's a call option, so it must be it's a call fixed. Since it's a fixed strike call, okay. So fixed strike call it means that something minus k. And since it's a look back option, so the underlying should be the money maximum. All right. So let's fix the look back call, or look back. Okay, fixed strike look back call. Okay. And the second part is a short position in this floating strike look back put. Okay. So it's a short position, and it's a floating strike put. Okay. So that means something minus st, and it's floating, so that's mt. All right. It's a put, so it means something minus stock price. For example, this floating because the strike price is always is chosen to be running maximum. Okay, and there is no positive part anymore because this maximum, historical maximum, is always greater or equal to the stock price and element. So that's our payoff for this portfolio A. That's the value. And you see, actually, this positive part is quite annoying. So we cannot do anything if there is a positive part. So if we can reduce this positive part, if we can get rid of this positive part, you will see is if there is no such positive part, you will get this kind of payoff, and MT minus MT will get cancelled, and what's left here is just ST minus K, which will be the same as the value of portfolio B. Okay, so is that always true from here to here? From the first thing, the first line to the second line, is that always true that we can get rid of the positive part? That's the only thing we need to focus here. And so in general, of course, we cannot do that. Okay, in general, we cannot do that. But here we got this additional condition here. Okay, we have this additional condition here. So this additional condition states that currently, if you at this time, your historical maximum is already larger than K. So that you will realize that by the maturity time, if you look at the whole historical maximum at the maturity time, this historical maximum will also be larger than current historical maximum. Okay? Since the maximum, the historical maximum, this number should always be monotone increasing along time. Okay? Since you have more observation of the stock price, so you can only update to get a higher level of the peak point of this sample class. Anyhow, the historical, this is the whole period. This is the whole period of maximum, and this is the previous period maximum. Of course, the whole period maximum should be larger than the first period maximum. So MT is always greater or equal to n. Okay, MT stands for the maximum of the stock price over the time from 0 to t, but this M, current M, stands for the maximum of the stock price from 0 to current time t. So longer period will always give us a larger maximum value. Okay, so the whole period maximum will be larger than the first period, the shorter period maximum. So of course this M is larger than K. That's in our condition. So we'll see this MT thing is guaranteed to be larger than K. So that MT is always larger than K, so that this positive part is actually useless. So we can just get rid of this positive. Okay. So once we can do that, you'll see everything get connected because portfolio A and portfolio B will have the same value at maturity, and it's guaranteed with probability 1. Okay. So that we know, as implied by no arbitrary principle or law of price, this two portfolio should have the same value anytime before that, as long as this condition holds true. Okay? So that's how we prove that for this question. Okay. Actually, it's a very similar question 4.4. So we are going to prove that this kind of certain relations between this option price. So this kind of option is a look-back spread call option. Price can be written as this call option plus this put option minus some cash. Okay. So our idea is very simple. It's very similar. This is the one our portfolio A. This is our portfolio B. As long as these two portfolios should give us will give the same value by the maturity time in the future, then at the current moment, these two portfolios should also have the same value. Okay, so this is our portfolio A, and this is our portfolio B, and our portfolio A value should be just payoff function of this option. Okay, just be this guy. That's the value of our portfolio A. So for portfolio B, let's work this out. Okay. So portfolio B consists of 1 unit of this type of call and 1 unit of this type of put and minus this amount of cash. Okay. So this call option will yield this call option payoff, of course. And what's the payoff? So that's a floating strike call. Okay, floating strike look back call. So floating strike means the strike price should be some stochastic process. Since it's a call, so that means the stock price, the payoff should be stock price minus something. And here it should be minus the running minimum. So that's the first part. Also, we want to add this positive part here because this is the lowest point of the stock price in the history. So current stop price should be at least this amount. Okay. So we do not need this positive part. And the second asset is a floating strike, look back put. So floating strike means the strike price is a random variable and its put feature, so it's something minus stop price. So it should be MT minus stop price. And we also don't need this positive part here. That's because MT is the historical, the highest level of the stop price in the whole history. Of course, it's just a moment. The stop price at maturity is just a moment, so it should be less. So this guy minus this guy is always positive, so it's not in the positive part. And this cash part is just, of course, become minus K. Because we're taking account of this interest rate R. So this amount of cash at time T becomes K dollars. Okay? So that's our for portfolio B, you'll see this ST minus small mt plus capital MT minus ST again. So ST and ST get cancelled. Alright, so that's a very, very clean formula for the portfolio value for portfolio B, the value of portfolio B. Alright. So immediately you may realize that this guy is the same as this guy. Okay? So in order to show that these two are the same, then we just need to show that we can get rid of this zero part, this positive part here. So we hope that this guy always equal to this guy. Of course, in general, it cannot be true, but we still have some very special condition here. So let's make some comparison, very simple comparison. So this is the current. So this is the current maximum, the current highest level. So in the future, when we look at the highest level of the stock price in the future, of course it could be higher, but it cannot be less. So MT will be larger than M. Okay. Also for small MT. That's the worst price. That's the worst price. So compared to the current worst price, if you like this stock to grow for some while, the worst case could be even worse, but it cannot get better. Okay? The smallest value should be even smaller. The lowest, the minimum stock price will be even smaller. So this number, comparing to these four numbers, you'll see we are going to increase this M to MT because MT is larger, and I'm going to reduce small m to a small number MT. Okay? That means comparing to these guys and these guys, I increase M to M capital T, I decrease M to M small t, and then K is just a constant. So of course everything will be larger. That means M capital T minus small mt minus K should always greater or equal to 0. Okay, because we have this condition here. So this guy is always greater or equal to 0. That means the maximum between these two is always the first one. 0 is actually, we do not care about 0. 0 can be taken off. So this guy. So the value of this portfolio A also equals to this one, and it coincides with the value of portfolio B. So two portfolios have the same value in the future. These will have the same price at the current moment. So that we prove this equality here. Okay, we prove this identity here. So you see, nothing. We do not need to know anything about these PDEs. We do not need to know how to evaluate some interpretation. Just by replication. And you could see this replication always just a log one price or this kind of portfolio thing. As long as we know some basics about this stochastic process, larger become larger, smaller become smaller, and of course payout structure. So that's everything, all the questions today. So to summarize a little bit, I guess since it's Asian option and Asian options and the look-back options, the basic type is already quite complicated. Okay, you see in the most basic type, without any extensions, in most cases we cannot find the closed form solutions, and even this PDE formulation is already very complicated, and of course it's not solvable. So I guess the question relating to this part will also not be that difficult. Just like this tutorial question says, just making use of very basic stuff, you can know that, you can do that. But the crucial, the most important part, I guess, is one of them is, of course, how do we derive this PD? How do we get this PD formulation? Okay, how do we get this PD formulation for any arbitrary pair of functions, of arbitrary options? Since this is just Asian, it's just a call as the look back. But in the most general sense, everything comes from this risk neutral, since it's a martingale risk neutral series, risk neutral pricing, risk neutral valuation series, and some to combine it with some Ito's lemma here, and you can derive this PD. Okay, so that's I guess it's one of the major message here. And some other useful techniques, I guess, is some very tricky step when we derive this geometric average Asian option. Okay, when we derive this pricing formula in closed form in the implicit way, we actually calculate this guy. We kind of calculate this guy. Okay, we kind of calculate the distribution of this kind of integral. Okay, it's not exactly the same because in your lecture you got WT minus W something like that, but very similar thing. Okay, we can calculate the distribution of this kind of integral is mean zero or variance whatever. So it's actually to get the variance of this kind of integral is not a very easy thing. Even in sometimes mean is also not that easy. I guess this kind of trick is very useful. It may not be that useful, but it's something we should learn at least, I guess. And very interesting stuff to look at. So in the general case, so if you actually it's very tricky to get this. If we add some even the most simple function, very simple function f, it's very hard to get the similar results. It's very hard to get the distribution. It's almost impossible to know what's the exact distribution of this kind of integral. So perhaps the only thing we can do is the integral of this guy. Okay. So if you're interested, you can try to see whether you can get this guy, the square of the integral. But I'm not sure you can get that or not. It's very hard, I guess, in general. So I guess it's some very useful tricks we can know. Okay, we can learn about. And when speaking of which, actually, it comes to my mind that some similar stuff we can try to compute if you are interested. Is that this x, okay, the distribution of this x. I'm not sure whether it will be quite related to our lectures, our assignments or anything. But actually, if you are interested, I try to solve the distribution of this xt. So you can try to find what is the mean and what is the variance of this xt if xt satisfies this kind of stochastic differential equations. Okay. I guess it's doable given your knowledge in this in the probability, this kind of stuff. Yeah. At least give you some idea that in this course we can still find the distribution of certain stochastic processes. Okay. I'm not quite sure whether it will be anything related to our option pricing theory or not. But I guess it's always a good practice for you to see whether you can really do some this very concrete computations here. And to build your capabilities in computing this kind of expectation, variance, etc., will really help you to find, in some cases you can find the closed form solutions of some option price. It's all about this calculation relating to this probability distributions or expectation and this kind of stuff. So I think I will end here, I'll stop here. And I believe we still have one more tutorials next week. So see you next week.